Okay, guys, so let's go over here. I need to go back to the problem because otherwise there's no way for me to finish it up, okay? So basically, let's see. Here we're doing problems about the Rankine cycle, okay? I'm guessing. I'm guessing no, because this is a Rankine cycle, okay? So now I cannot remember. So this is a Rankine cycle. So we say Rankine cycle is the main model in order for analyze steam engines, okay? Here's a steam power plant. So you can think about a nuclear plant, okay? So in the nuclear plant, the nuclear energy is used as the boiler, no? But everything else should be about the same, okay? So this is the typical representation. So you need to have water, cold water. Obviously, you need to pump it into a boiler. Once you boil it, you're going to put it into a turbine, which is the one generating the energy. Water is going to come back. You need to cool it down throughout the condenser, and you go back throughout the cycle, okay? So if you do this, if you look at the figure on the TS or TV diagram, basically that's what we have over here. Here you go to the pump, all right? So you increase the pressure through the pump. You go from 1 to 2, so P3 equal P2 as well. 1 to 2, now you keep heating over here. You need to heat a little bit, and then you get here on the boiler. And I think on the first case, I did the ideal case where the minimum temperature you need is just a saturated temperature, but in this case, the temperature was a little bit higher, no? I think that's where I'm confused. So now in the turbo plant, you know that it will be isentropic. So you go back to this point, and now at constant pressure, you get into the condenser, and there is where the water gets cool. So what do we need to solve for in this problem? I don't know, but this is the figure. So it looks like probably we needed to find, the properties. So for P1, we needed to know two things. So at P1, we know it's going to be the saturated liquid, and we knew the pressure. So we could just go to table A3, and here we found H1. We needed S1 to find S2. Okay, now remember, we need F2 in order to find what will be H2. Okay, and this is the part that's important. Hopefully I'll put it on the next page. Now over here, yes, is that basically because of the lack of tables for this region over here, all right, over here, we know that the change here of the power needed to run the pump, which is this one over here, all right, the power that you need to run the pump, is we know it's equal to H2 minus H1 times M, but this could be approximated by P2 minus P1 times V1. Okay, so why is this helping? It's because now from this figure, you know that P2 and P1 basically are known, because P4 equal P1 or P1 equal P4, and P2 will be equal to P3 because this is a line of constant pressure. So knowing that the power here is just equal to the change in pressure times the volume over here at constant volume. So we go to this page. We are able to solve if we go to able to solve for this expression, that will be the total amount of power. And we know this one was equivalent to this one, H2 minus H1. So we're able to solve for H2 that was equal to H1 plus that quantity here. Okay, that was one of the things that we needed. So here, and here's where I find out that I think that was the last page or not. Yeah. And here's where I find out that I did a mistake on my figure, because here they give us P3 equal to 3 megapascals, which was 350, no? But then when we went to the tables, we found out what? That the critical temperature of this point wasn't 350, but it was 233.9. And that's when I say, okay, sorry guys, but I should have checked maybe that before doing the figure. Really 0.3 is not here. It is a little bit higher than this critical. So really the process is from here to here, here to this point, and this line should not be here, from here to here, and from here to there, no? Okay, so So if I correct this figure, basically this line should not be here, okay? All right, so we stop over here. We needed to find H3, so let's H3. So we know H3 is in this area, so that should be the superheated tables, no? So I think it should be table A4. So here we should go to table A4. We know the pressure 3 megapascals and 350. So if we do that, what do we get? So okay, SI tables, here we are. Should be a 1A2 is the one that has the double columns. Here we go. So we have, what do we have? 3 megapascals. So this is in bars, so 0.3, 5. We are out of luck. So we have 5, 7, and 0.3. It jumps from 0.3 to 5. Okay, so I guess we're gonna have to do a strange interpolation, no?
Wait, isn't it's 3 megapascals 30 bars?
I'm just reading here. So it's 3 megapascals. Okay, yeah, I was looking at the bar. Sorry, good. So yes, good. I didn't want it to interpolate. So that's good. Here we are, 3 megapascals. We are good. Oh, but we don't have 350. Okay, so and here, so what do we need to do? We need to interpolate. So we're gonna have to interpolate between 320 and 350, no? Okay. So the value that we want is the H. Do we need also the S? Probably we need the S as well. So let's see. Let's do both. I think we're gonna need H and S. So it's the last two values. So 30 between 320 would be all these values here. Okay. So there we go here. All right, so forget about this H3 here. We need to interpolate. So table A4 at P equal 3 megapascals. Okay, so we have a temperature 320. I think we had, and a temperature 360. This will be T8, T sub B, H sub A, H sub B. And then here we'll have S sub A, S sub B. So we're gonna have H sub A equal to 3,043.4. S H sub B 3,138.7. S sub A 6.6245. And S sub B 67801. So basically, I hope by now you don't need this figure, but interpolate will be between A and B. This should be the temperature, and we're trying to find is H or S. So I write the equation, but you give me the value. So we have H sub 3 should be equal to what? H sub A plus H sub B minus H sub A divided by TB minus T8 times 350 minus T8. And here you can give me the value for H sub 3. And S sub 3 would be H sub A, S sub A plus S sub B minus S sub A, TB minus TA, 350 minus TA, and this will give us S sub 3. Okay, so some of you did a calculation. We get H sub 3 equal to 3,114.875 and S sub 3 equal to 6.7412. All right, so now we need to go back to the figure. So now what is the problem? I mean, not the problem, but what's happening? We are superheated, and because we're going to go to the condenser, so 3 to 4 at the exit of the condenser, what's going to be the state of the water? Is going to be a mixture, okay? Because it's between these curves. So if it's a mixture, we need to find out how much of the mixture is in the gas form and how much is liquid, which means that we need to find the quality factor X4, okay? So in order to find X4, what do we know? We know S3 will be equal to S4 because through the turbine, it is isentropic. Okay, and what else do we know? We know the pressure is 75. So that's the two things that we know about state 4. So let's go and do that. Yeah, so let's go and do that. The what? Okay, so basically we have at 4 to find H4, we know that S4 will be equal to S3, which is equal to 6.7412. And we know that P4 is equal to 75 kilopascals. So one expression to find the quality factor is what? So we know S of 4 should be equal to what? S of fluid plus X of 4 quality factor. And this is what I think is S fluid, no, S gas minus S fluid. Yeah, I think it's S gas minus S fluid. Okay. What is that relation? That relation should be, let's see if it's over here. Remember, I told you that. Oops, that's not what I want. This one, I'll give you this handout. Remember, this is a different expression we have. So it's actually S sub G minus S. I'm using this one to find X. So from this equation, you can solve for X4 will be equal to what? Will be equal to S4 minus F sub F, S sub G minus S sub F. From where do we get S sub F and S sub G? We need to get it probably from table A2, no? Which is one of the pressures. So from table A2, at P equals 75 kilopascals. From here, we should get S of fluid and S of gas. So let's go. I'm thinking it's table A2, okay? But we can check. So page up. This one is table A3 or table A3. Let's see, table A2 is the table A2 is the temperature. So it's table A3 actually. So instead of table A2, write down table A3. And the pressure is in bars, and this is kilopascals. So how many bars you have here? The transformation is the kilopascal. So we have 100. So we need to have that in bars.
Would be 0.75. Yeah.
So it will be 0.75.
Yeah.
The one we don't. Okay, so that means, but it's fine because right in the middle, we can just add up and divide by 2, no? So if we go at this one, please, we need to find the S value, these values are here. So can somebody do for S sub F 1.1919? What did I do here? Yeah, I don't know what I did. So is 0.75. So 0.1919 plus 1.2329. You add them together and you divide that by 2, and that will be at 0.75, no? 1.2124. Okay. And for S sub G, we do the same thing. You do 7.4797 plus 7.4346 and divide that by 2. Oh, they give us here the pressure in bars. Actually, we had it at the end. You see? Just realize.
I get 7.4571.
4.
4571.
4571. Okay, so now that we have that, we can substitute into this equation so that x4 will be equal to what? S sub 4 will be 6.7412 minus 1.2124 divided by 7.4571 minus 1.2124. So this will give you a quality factor of how much? Oops, sorry, let me go here. So this is basically what I've done. I substituted the data. So somebody give me the value of 0.885. So that means that 88.5% of the mixture is gas. Okay, or it's vapor. And the rest is liquid. All right. Okay, so now this again, not very convenient. So you have to do it for me again, but let's go to the next page. I'm not clear about this interpolation, but we're gonna have to do another one again, another interpolation again. So basically now we have H4 will be equal to what? Will be equal to H fluid plus X4 H gas minus H fluid. From where do we get H fluid and H gas? Same as before, from table A3 at P equals 75 kilopascals. But what's gonna happen? What's gonna happen? We're gonna have to interpolate. So I need again your assistance. So this time your assistance will be for H sub F and H sub G. So what do we have? So we need to add and divide by 2. So 0.75 will be, please do for H sub fluid, do 376.7 plus 391.66 divided by 2. What do you get over there? 380 what? So 376.7 plus 391.66, that's equal to
384.18.
380.
384.18.
Okay.
I got 384.15, so yeah.
Okay, it's fine. I mean, you could get the same thing. You are plugging the same values, I hope. So, and HG would be what? 2,660 plus 2,665.8. So that's what? 5.8 difference.
I got 2662.9.
2,662.
62.9.
6. So wait, okay. Sorry, no. So it should be. Sorry, but so it would be 2,000. Give me a value. Would be 2,000 what?
2662.9.
Okay. So 2,662.9.
Yes.
Okay. So now we can substitute into H4. Should be equal to 384.18, or I don't know, somebody said 15, but plus 0.885 times 2,662.9 minus 384.18. And this should give you H4. Okay, so we get 2400.8472. We can put 2400.85. And okay, so it was page 118. And what we had to do in this problem is to find the efficiency. So last class, we did derive that efficient, two expressions for the efficiency. We had that the efficiency of Rankine cycle could be equal to what? Q in minus Q out divided by Q in, which was equal to 1 minus Q out over Q in. And we knew this was equal to 1. So the Q out is equal to the change in the entropy H1 minus H4. We can go and check on the figure. So from this figure, what do we have? This should be the Q in, no? We are boiling the water. This should be the Q out. So Q out is in function of H1, H4, which is what we have over here. Wait, the last page. H1, H4, and Q in should be in function of what? 2 and 3 in the boiler. This is H3 minus H2. Okay, so that means that the efficiency is going to be equal to what? 1 minus what do we have for H1? For H1, we had 384.18 minus 2400. So that's why we take the absolute value, 2400.8472. And we divide by H3 that we found to be equal is the one we just did, 3,114.875. So 3114.875 minus H2, that is equal to what? 387.21. Okay, that's the one we found. But this is H4, H2 was over here. 387.21, right at the bottom here of the page. Okay, so if you do the calculation, let me know what you get. Okay, so we get 0.261 or 26.1%. Okay, this is just for you to check, but we also have from the class notes, okay, that the efficiency, you could have calculated that one using what relation? H3 minus H4 minus H1 minus H2 divided by H3 minus H2, okay? And I'm gonna go back, is what we did last class. But I'm pretty sure you should get the same thing. You can go and check. Somebody had a question about the assignment, so let's go to that stuff. So assignment 8, and I might add an assignment because we're doing really good in time at the end. So assignment 8.
That's not the right class.
That's not the right class, so we're not going to find it there. I know this is vibration. So modules, I can go just to assignments, I guess, no? Assignment 8. So this is chapter 5. There's only 2 problems?
Yeah.
So, okay, so there's an air within a piston cylinder assembly. Okay. All right, so let's do this one. So it's problem 553. So I'm just doing that. Just copy the figure, even though I don't think we need it, but just do the figure. So TH, T cold. So we have 1, 2, 3, 4. This is T cold. This is T hot. And what's important to know is that this is a Carnot heat pump. As shown in the figure for the cycle, TH is equal to 400 Kelvin. T cold is equal to 300 Kelvin. The energy rejected by heat transfer at 400. Okay. So if you want, Q34 is 250 kilojoules per kilogram. The pressure at the standard of the isothermal expansion is 325. So what is the 325? The pressure at the start of the isothermal expansion. So both of them was an expansion. So expansion is 1 to 2, no? Yeah. Volume increasing. So I guess expansion is the volume increases. So P1, P2, I guess that's what they give. So P1 is 325 kilopascals. So that's at T cold. Okay. The magnitude of the network in kilojoules per kilogram of air. Okay. Let's do this stuff. So there we go. Okay, so what I need to do is I need to understand what's going on here. So personally, for me, Carnot cycles is always between two different pressures. So if you ask me to me like this, I like to do this, okay? I don't know where would be each one of these lines, but just what I do. So it looks like this is T, V, we have here PV. These should be lines of constant pressure.
The first graph is PV. Yeah, first one. That's what it said on the assignment.
Oh, this one is PV?
Yeah.
Okay, so PV. So this is the TV. Yeah, this is correct. TV going through lines of constant pressure. Okay. So I don't know what would be 1, 2, 3, 4. But what's important here is that all this stuff is based on what type of figure. That you have a hot here, you have a cold over here. Here you have your cycle and a heat pump. They say this is a Carnot heat pump. So what is the function of the heat pump? To remove heat, no? This will be Q hot, this will be Q34. And now this one here, so the heat goes in that direction. This should be what? Q12. And in order to have a heat pump, you need to provide power. Okay, so when we look at the heat pump, remember if it was an air conditioning system or refrigeration system, we look at the bottom part, no? For here, we look at the top part. So I don't remember, I think you showed me what is the symbol they use for the efficiency. Is it gamma?
Yeah.
So basically gamma is what are we trying to achieve? We're trying to get heat out, no? Okay, so it should be Q dot 34. And in order for that to happen, what do we need to do? Provide power. Okay, so basically it will be the efficiency. So we know the hot reservoir will be at TH. The cold reservoir will be at T cold. So since they mentioned the term Carnot cycle, this means that this is for an ideal case. Okay, so you show me your solution here. So this should be equal to what?
T hot divided by T hot minus T cold.
So this is T34 is this one is T hot. Okay.
And then divided
And
by,
then the maximum work you can get, this is the big thing, is the difference in the temperature between the hot and the cold reservoir, no? So this will be TH minus T cold. But this is not an equation that you need to memorize. This is understanding. Okay. I don't memorize any of these equations. That's why I needed to do this figure. Okay. So from this figure, what do we need to solve in this problem? Is 4-day, well, I keep going there, the magnitude of the next of the work input, okay, in kilojoules per kilogram. So what does that mean? We need to solve for this one, no? Okay, so from these two expressions, we can find then that the power will be equal to what? Q dot or Q34 is not Q dot, it's Q34. This is a closed system, Q34 times what? TH minus T cold divided by TH. So if we do the numerical application, what do we get? This again, remove the dot. There is no dot. So it should be equal to Q34 is given to be 250 times 400 minus 300 divided by 400. So we get 250 divided by 4. Yeah, will be 62.5. We don't need to plug the numbers, 62.5. Basically this is 100. So it's 25, okay, well, 62.5, okay? Is that what they had over here? I don't know, but I mean, it's not important, the values, I always tell you, 62.5, okay? Now, what is the next thing we need to do? What is part B? Oh, the pressure at the end of the isothermal expansion. The pressure at the end, so we need to find P2. Okay. Okay, so this problem is not obvious at all, I have to agree. So let's see what they did. Is as follows. So I'm page 120. So basically what I'm saying is that we need to find what happens at P2 over here. So this cannot be P2 because so this is incorrect. This is not correct. Because P2 is a change in pressure, and here I do it at constant pressure. So that figure I don't think is correct. Okay. So anyway, so what we're doing is for process 1, 2, we know that the work for 1, 2 per unit mass will be equal to P. I mean, we can do volume, would be PdV. I don't think we need to do this. Because we are dealing with an ideal gas, what do we have? PV equal to N RT. Would be the R bar or no R bar? I don't know about that, but
No R bar.
No R bar in this case. Okay. So from here we can write down that P is equal to nRT divided by V. Okay. So if I substitute into that equation, we have work 1, 2 equal to integral of nRT dV over V. And this is between V1 and V2. So this is going to give us that this is equal to nRT log V2 over V1. Okay. The other thing they do is that they say that using the ideal gas relation, we're gonna have P1 V1 equal to N RT1 and P2 V2 equal to N RT2. So if we do, so this will give you what? P2 V2 divided by P1 V1 will be equal to NR T2 divided by NR T1. So this comes at the ends.
T2 and T1 are also the same. They're both TC.
So, okay, so from the figure here, between 1 and 2, this is isothermal. So that means that it's equal. So we'll say T1 equals to T2. So basically here we're gonna have that then P2 over P1 equal to T2 over T1. No, sorry. P2 over P1 will be equal to V1 over V2. So substituting into the star equation, we're gonna have that N R T, and here we need to be called what this will be T cold log V2 over V1 will actually be equal to nRT cold log. So this is reverse P1 over P2. So let's call that relation here on a double star. And then what is the last thing to do? So in addition, if we apply the first principle of thermodynamics, we have Q12 minus work 12 should be equal to the change in internal energy between 1, 2. Okay, we know that for an ideal substance or ideal gas, it should be equal to what? This is equivalent to CV T2 minus T1. Correct? Because an ideal substance. So in this case, since T1 equals T2, what will happen to this? This is 0 because T1 equal T2 equal to T cold. Okay? So that means at the end that we're going to have what? Q12 will be equal to work 12. Okay, and from this expression here, what do we have? We had Q34, remove the dot again, Q34 equal this, but this should be equal to what? Whatever is the hot temperature minus what the absolute value of Q12 minus Q. Or actually it could be vice versa, no? Let's just put the absolute value here. We'll find out. So at the end, we can get here that Q12. Yeah, let's see, should be equal to what? So this should be Q34. Sorry for that. It should be Q34 minus Q12. Or let's see if we can do it with the sign convention. So power going in will be negative. Oh, can leave it that way. So this will be Q12 should be equal to what? The work plus Q34.
I got 312.5 from that.
Okay, but basically what we generate here is what? 6 minus 62.5 because it's coming in. Work coming in. Now we go with the same convention, but it doesn't matter. Plus the Q34 is the heat going inside the system that is equal to 250. So what is the difference?
So I got 187.5.
So Q12. So for that, okay. So Q12. Let me go to the next page. So Q12 is 187.5. Yeah, kilojoule.
187.
Okay, now from this relation, what do we know? Work 12 is equal to this expression. Okay, and work 12 will be equal to Q12. So we're gonna have, so combining above equations, what do we have? Work 12 equal Q12 equal to nRTC log P1 over P2. So we know Q12. So it gives you Q12 divided by nRT cold equal to log P1 over P2. I don't know how they did it, but here, now if you put the exponential, what do you get? P1 over P2 will be equal to the exponential of Q12 divided by nRT cold. Or what are we trying to find here? P2 or P1?
P2.
So P2 will be equal to P1 divided by the exponential of Q12 divided by nRTC. And what is the letter N here? The letter N over here is the number of moles, no? So the letter N over here would be mass over molar mass. This R here should be the universal gas constant. I mean, you should go and substitute over there, no? So basically, you see here, they solve for this and then they take the exponential, but basically, I mean, you're not going to get 76.1, but you should get something different. But this is the procedure. I mean, does that make sense or no? Yeah, that one wasn't easy, yeah? Yeah, that was not an easy problem.
Yeah, no, I got the right answer. 36.8.